SpaceX is launching the 13th Starship flight test, sending up those V3 vehicles and carrying 20 next-generation Starlink V3 satellites into orbit for the first time. But they're doing it just to intentionally vaporize them in the atmosphere.
Yeah, I mean, you look at that operational choice and you realize they're really forcing the hardware to work a lot harder this time around. Testing an empty vehicle just proves the basic physics, making sure the tanks hold pressure. But flying with live payloads while actively trying to fix mechanical failures from the last run, they're intentionally compounding the stress on the vehicle.
Right, because adding live cargo just completely alters the risk profile. You aren't just gathering telemetry on your own fuel tanks anymore. You've got actual functional hardware in the payload bay that needs to interact with the vacuum of space. So the rocket has to perform its primary job as a heavy lift vehicle while still acting as this high-altitude testbed.
Exactly. So what does it actually take to push a rocket from merely surviving a launch to reliably delivering cargo and returning intact? Because survival is just the baseline. I mean, you can survive a crash landing, but reliability requires this brutally difficult level of precision, especially when you're trying to land a skyscraper back on the exact pad it launched from.
Well, the super heavy booster from the previous flight is a pretty clear example of how fast that precision breaks down. During stage separation, they had these slight differences in the engine startup sequence. And that tiny variance in timing caused the directional flip of the booster to be off by about 90 degrees.
Yeah, that 90-degree error just shows how unforgiving orbital mechanics are during hot staging. You've got the upper stage engines igniting while the booster is still attached and firing its own engines. So there's this massive blast wave slamming directly into the shielded top dome of the booster. Even a slight asymmetry in thrust just physically drags the massive piece of hardware off course before the flight computer can even register the attitude change.
And the problems just compounded from there. After that inaccurate flip, the booster tried its boostback burn to push back toward the launch site. But 5 of the 33 engines actually failed to relight. Without those 5 engines providing thrust, they just had to end the burn early.
Which is a critical issue. If the booster can't reliably flip and complete that full burn, it simply cannot reach the offshore landing point in the Gulf of America. The geometry of the flight path is strictly governed by gravity and momentum, so ending the burn early just means falling significantly short of the target coordinates.
So to fix that precise issue, they've implemented a new startup sequence for this flight that's supposed to be way more robust to timing variability. The software anticipates those slight delays and adjusts the thrust vectors to flip the booster more reliably. It's almost like a highly coordinated symphony, where if a single instrument plays off beat, the entire orchestra loses its balance because the systems are so interconnected.
Right, and I have to point out that's exactly why the updated engine alarms and abort logic they integrated for this flight are tailored to match that exact reality. In a multi-engine flight environment, the acoustic and thermal environment is pure chaos. The software sensors have to instantly differentiate between normal violent vibrations and the specific harmonic signature of a single turbopump failing, and then shut down a bad engine before it damages the ones next to it.
Man, and if the booster is that sensitive, the upper stage must be taking an absolute beating when it pulls away from the stack. We saw that vulnerability play out clearly when the Starship upper stage lost a Raptor vacuum engine right after stage separation on the last flight, which creates a severe thrust asymmetry.
Yeah, but the silver lining there is that despite losing the vacuum engine, the ship still reached its planned suborbital trajectory. Demonstrating true engine-out capability in flight is a major engineering hurdle. It proved the flight software can survive a critical failure mid-ascent, rebalance the thrust from the remaining engines, and still hit the target coordinates.
If you're not subscribed yet, take a second and hit follow on whatever podcast app you're using. It helps us keep making this. We appreciate you being here. So, looking ahead, the immediate next step on this flight is deliberately relighting a single Raptor engine in space before they head for a controlled splashdown in the Indian Ocean.
Doing that in a vacuum introduces some serious risks. You have propellant sloshing around without atmospheric drag to help settle it in the tanks. They have to rely on small ullage thrusters to push the ship forward, just enough to force the liquid methane and oxygen to the bottom before trying to ignite the main Raptor.
And hitting that planned trajectory means they can actually put something to work in space this time. They're carrying 20 of those Starlink V3 satellites, which are supposed to extend their arrays and try connecting to the larger constellation using high-capacity lasers.
But the interesting detail is that because they're on a suborbital trajectory, those satellites aren't staying in space. They are entirely disposable. The trajectory guarantees they will be destroyed upon re-entry shortly after deployment.
Which really makes you wonder, why would SpaceX put fully functioning laser-equipped satellites on a suicide mission? Why not just use dummy weights to simulate the payload mass instead of throwing away highly complex functional hardware just to test the deployment mechanism?
Well, 6 of those sacrificial satellites actually have a specialized suite of cameras on them. Their whole operational purpose during that brief window of freefall is to act like orbital paparazzi. They physically scan Starship's heat shield from the outside and transmit those high-resolution images down before they burn up.
Oh, and the physical setup on the ship itself makes that inspection easier, right? SpaceX intentionally painted several tiles white to simulate missing tiles. That creates high-contrast imaging targets against the black thermal protection system, making it much easier for those satellite cameras to track the ship as they drift away.
Exactly. The ultimate goal is testing methods to analyze heat shield readiness while the vehicle is still in orbit. Because if you want to return a massive ship safely over land in the future, you have to know exactly what condition the thermal protection system is in before hitting the atmosphere. You can't just rely on internal sensors.
That definitely explains the intense scrutiny from the satellite cameras, especially since SpaceX is actively altering the heat shield and intentionally pushing its physical limits on this flight. They've attached multiple new tiles directly to the metallic side of the aft flaps and put modified tiles with new attachment mechanisms on the aft skirt.
Right, and they installed load-sensing tiles directly into the heat shield because they're deliberately flying a trajectory designed to generate higher dynamic pressure on ascent. They want to gather real-time flight data on how those different physical attachment options hold up when they put maximum crushing force on the exterior of the vehicle.
So by altering the pitch and velocity profile, they're essentially trading a smoother, more fuel-efficient ride for increased payload to orbit capacity. They're prioritizing sheer acceleration and deliberately putting more stress on the tile attachments to find exactly where the physical breaking point is.
Yeah, and the conversation around the whole development program shifts when you see this. It demonstrates a move from simply trying to keep the rocket alive to actively using it as a disposable laboratory. They are throwing fully functional satellites and experimental tile configurations at the vehicle just to test the absolute limits of its physical design.
You really have to wonder how many more of these diagnostic suicide missions it will actually take before the heat shield design is fully validated for a true return to the launch pad without needing a camera crew of disposable satellites checking its work in orbit.
If you're not subscribed yet, take a second and hit follow on whatever app you're using. It helps us keep making this. We appreciate you being here. Also, check out our YouTube channel for more business and tech updates. There's a link in the description.